Okay, just imagine this for a second. A robot that doesn't just walk across a room, but can actually use its hands to do complex stuff, all at the same time. Today, we're diving into how the Unitree G1 humanoid is making that a reality, and it's doing it by tackling one of the biggest, baddest challenges in all of robotics, loco-manipulation.
So here's the big question, right? How can you possibly get a machine with 37 different moving joints to walk, reach out for something, and carry it back, all without just falling flat on its face? I mean, it sounds simple enough for us, but for a robot, this is the equivalent of a high-wire act. It's a symphony of coordination and control that's really pushing the limits of what we thought was possible.
All right, let's really get into why this is so tough. The real challenge is that the robot has to manage dozens of conflicting goals every single millisecond. You know, try patting your head and rubbing your stomach at the same time? Well, now imagine doing that but multiplying it by a dozen different tasks, all while trying to balance on one foot. That's pretty much the world a humanoid robot lives in.
You can just forget about those clunky stop-and-go robots you might be picturing. You know, the ones that would stop, think for a second, move an arm, stop again, and then maybe take a step? Nope. Today's humanoids are all about fluid, simultaneous action. It's a concept called whole-body control, and it is a total game changer. It lets the robot move and act like one single cohesive unit.
So how in the world do you conduct this orchestra of motion? Well, in robotics, you need one controller to rule them all. And for the G1, that's a whole-body controller that's powered by something called quadratic programming. Think of it as the one ring that binds all the robot's joints and tasks into a single harmonious whole.
So what is this quadratic programming, or QP, thing anyway? Well, the simplest way to think about it is like a super smart GPS for making decisions. You give it all your destinations at once, like rule number 1, don't fall down. Okay, now reach for that box. And, oh, also take a step forward. And it instantly calculates the single best route, the most optimal set of motor commands that gets everything done without causing a crash.
Now, here's where it gets really clever. It's all about priorities. See, not all tasks are created equal. By assigning a massive weight, like 1,000, to balancing, the controller fundamentally understands that staying upright is absolutely non-negotiable. It will never sacrifice its stability just to reach an object a little bit faster. It's basically a mathematical survival instinct built right in.
And this whole calculation happens at a blistering pace. I mean, blank and you'll miss it hundreds of times over. This controller, using an open-source solver called OSQP, makes a brand new, perfectly optimized decision for every single joint in its body 500 times a second. That's a complete recalculation every 2 milliseconds. It's that incredible speed that lets the robot react to the world in real time.
So what does this actually look like in practice? Well, it's kind of like a 4-step dance that repeats 500 times every single second. First, you've got the state machine acting as the director, deciding the big picture goal, like walk. Then Pinocchio, the robot's internal physicist, calculates all the exact dynamics, where every part is, how much it weighs. That data gets fed to our QP controller, the brain, which solves for the best possible joint torques. And finally, the MuJoCo physics simulator brings it all to life in a virtual world. And then, boom, the loop starts all over again.
So if that QP controller is our star dancer, executing these flawless moves with incredible speed, then the state machine is the choreographer. It's the mastermind planning out the entire performance from start to finish. It's what makes the difference between just a random series of movements and a beautiful, coordinated ballet with a real purpose.
And here it is, the full performance. It's like a 5-act play of robotic precision. First, the robot walks up to the cable. Then, it pauses just for a moment to get stable and extends its arm. It grasps the object, lifts it, and then, and this is the cool part, it walks backward with its prize before gently setting it down and retreating. Each of those phases is a whole new set of instructions for that QP brain to solve.
And here's one of the most brilliant parts of the whole thing. The second the robot picks up that object, its entire center of mass shifts, right? But the controller doesn't even skip a beat. It instantly recalculates the new combined center of mass for the robot plus the object and subtly adjusts the robot's entire posture to keep that new point perfectly balanced over its feet. It's incredible.
Now, of course, a system this ambitious doesn't just appear out of nowhere. No way. It's actually built on a really solid foundation of research. It's the culmination of crucial lessons learned and technologies that were proven in a whole series of earlier experiments and labs.
You can think of this project like a greatest hits album of robotics research. The core physics model came from Lab 3. The ability to actually grasp something, that was figured out in Lab 5. Lab 6 gave us that choreographer, the state machine, and that all-important ability to walk, the gait generation itself, that came from Lab 7. It's just a perfect example of how real progress is made by putting all these proven ideas together.
So, when you see the G1 robot in action, you're not just watching one clever program. You are witnessing a symphony of systems. You've got a high-level choreographer, a lightning-fast mathematical brain, a super-precise internal physics model, and a deep foundation of robotics principles, all performing in perfect harmony.
All right, so let's just quickly wrap up the key ideas here. First, whole-body control is the art of juggling everything at once. Second, a weighted QP controller is the secret sauce for doing it safely because it sets clear priorities, like balancing is more important than reaching. Third, this amazing performance needs a whole team, the choreographer, the brain, the physicist, and the physics world. And finally, just remember that this kind of breakthrough is built by standing on a foundation of simpler, proven concepts.
This is about so much more than just robots in a lab. It's about the future of work, of automation, and really our world. So as these incredible machines take their first few steady steps, it really makes you wonder, doesn't it? Now that they can walk and work right beside us, what are we going to ask them to do next? What will we build together?